In this problem, the ultimate goal is to take a known energy for a rotational mode of a carbon monoxide molecule and use that to find the rotation rate in rotations per second, or we could even call that a unit of frequency. We can call it hertz. Now, this problem is just a first approximation, and the issue is that the number I gave for the diameter of the molecule is only accurate if the molecule is not spinning. If the molecule begins to spin, then the bond between these two atoms will start to stretch and it changes the distance. So this is a phenomenon called centrifugal distortion by the physical chemistry people. So let's proceed somewhat naively with our first approximation. In part A, I'm asked for the center of mass of the molecule using the oxygen atom as the origin. So let's go ahead and put a little origin on the oxygen atom. There it is, and that means the x value of that oxygen atom is 0. And if I look at my carbon atom, my x value there is going to be 1.13 times 10 to the negative 10 meters. So then I just plug into the center of mass x coordinate formula. So x center of mass is 1 over the total mass times m1 x1 plus m2 x2. And maybe I'm referring to oxygen as M1 here. So a convenient thing about putting the origin there is that it makes one of these terms vanish. So the x-coordinate of the oxygen was 0. I don't have to worry about that term. Now the big M here is the sum of both masses. So let's start plugging stuff in. The mass of the oxygen atom is 2.66 times 10 to the negative 26. For the carbon atom, 1.99 times 10 to the negative 26. And I'm going to factor out the 10 to the negative 26. So I don't have to write it twice. All right, then I have this leftover m2 times x2, so that's the mass of the carbon atom. So 1.99, 10 to the negative 26, multiplied by the x-coordinate, which is 1.13 times 10 to the negative 10 meters. And I factored those 10 to the negative 26 out because I knew they were going to cancel, so I don't even have to worry about that. So now I calculate 1.99 over 2.66 plus 1.99 multiplied by the original separation of the atoms, 1.13 times 10 to the negative 10. And when I do that, I get 0.4836 times 10 to the negative 10 meters. Now I chose to express this with a power of 10 to the negative 10, even though my calculator listed it as 4.8 times 10 to the negative 11, because it makes it easier to compare to my original distance. So apparently this right here is 0.4836 times 10 to the negative 10 meters. You should verify that that's less than halfway between the two atoms, because that oxygen atom is more massive. The center of mass should be closer to it. In part B, we want the moment of inertia of this molecule about an axis passing through the center of mass and perpendicular to the line connecting the two atoms. So if this thing is spinning, this center of mass point is going to stay stationary, provided the molecule is relatively isolated. And I need to get the distances between each of these atoms and the rotation axis if I'm going to compute a moment of inertia. Well, I already have this one. This one's 0.4836 times 10 to the negative 10 meters. Now I need this one. So I just take the total distance and subtract the 0.4836 times 10 to the negative 10 part, and I get 0.6464 times 10 to the negative 10 meters. Now I'm ready to compute my moment of inertia. So that's the sum of all the masses multiplied by their distance to the center of rotation squared. So I take my oxygen mass, 2.66 times 10 to the negative 26, and I multiply by the distance to the center of rotation, 0.4836 times 10 to the negative 10, all squared. And I take my carbon mass, 1.99 times 10 to the negative 26, distance to the center of rotation, 0.6464 times 10 to the negative 10, all squared, and I smash those numbers into my calculator. And when I do that, I get 1.454 times 10 to the negative 46 kilogram meters squared. So I'd like to point out at this point that a kilogram meter squared is an enormous amount of moment of inertia compared to what we're talking about here. So we're talking about individual atoms in this super tiny little molecule. A kilogram meters squared is the same as the moment of inertia of a kilogram sitting at the end of a meter stick. And we're talking about a single carbon monoxide molecule, so of course I have this enormous negative exponent on this. All right, let's look at part C. The lowest rotational mode of carbon monoxide has an energy that's known to be 7.62 times 10 to the negative 23rd. Get the angular velocity at this energy. So I'm going to write down K rotational is 1/2 I omega squared. And to solve for omega, so multiply both sides by 2, divide by I, and square root it. And omega is going to be 2K over I square rooted. Plugging in my numbers, that's 2 times 7.62 times 10 to the negative 23rd joules over this moment of inertia that I already computed. And when I smash those numbers into my calculator, I get 1.024 times 10 to the 12th radians per second. We're talking about some pretty fast spinning here. So of course that bond is going to stretch in real life. I want to convert this to rotations per second, which I could also say is hertz. It's a frequency of rotation. So I'm going to take this value and divide it by 2 pi because there's 2 pi radians per rotation. And when I do that, I get 1.63 times 10 to the 11 hertz, which I could then write as 163 times 10 to the 9 hertz, which is a gigahertz. So 163 gigahertz. Now I happen to know the real answer for this is 115 gigahertz. And it's because we've totally ignored the centrifugal distortion idea. But this is a good first approximation.